Hi, I'm Kwabena, CEO and co-founder of OpenMV, and today I'm here with Zach Shelby, CEO and co-founder of Edge Impulse. How are you doing, Zach?
Hi, Kwabena. I'm doing great. I'm glad to be here with you on your video show.
hmm
I was happy to nerd out.
Yeah. How are you doing? How's Edge Impulse doing? What's been going on?
Edge Impulse is great. We just saw each other at CES.
Yeah. hmm
CES was an amazing kind of cross-cut of everything that's going on right now in our world.
hmm
And we just saw embedded AI in everything. We saw it all across the consumer
hmm
device on display, much more than last year. We saw it all across wearable health devices. And then we saw a lot of computer vision built into everything in automotive, everything in robotics,
hmm
or more computer vision being part of these smart products.
Yeah.
And so interesting sign was that, we were fully booked with meetings, right? People at CES wanted to meet.
Yeah.
And so we did that across several partner booths, a lot of great demos going in the same time.
hmm
We had some demos that were OpenMV based as well, so that was cool to see. So it was great to run into you at CES. But yeah, coming out of CES and now soon going into embedded world, it feels like the sky's the limit. We really have a lot of amazing things going on. A
hmm
lot of platforms. We hope to announce some cool new platforms soon. We're going to talk about a couple of yours today.
Yeah.
Some very cool new model architectures that we have coming, and we can talk about that soon.
Okay. And Edge Impulse, you guys set this company up really to bring AI and make it easy for embedded devices. What was the pain point originally when Edge Impulse was started over 4 years ago now, right?
5.5 already. Time
Yeah,
flies.
yeah.
Yeah, 5.5. Yeah, so I've always been working in embedded systems since early in my career.
hmm
And my first startup was, stacks for communications and security in
hmm
IoT devices. And then I went to work for ARM. And at ARM, we started exploring much more widely in, my basic thesis for running developer open source activities was, what are we going to do with all this compute? It's kind of like,
hmm
what are we going to do with all this beer, right?
hmm
Who's going to drink it? Kind of a similar problem in compute. We saw where Cortex-M and Cortex-A architectures were going. Way too much compute
hmm
for the workloads that we traditionally code by hand, right?
hmm
There's only so much math that you can manipulate to use all that, and kind of running out of the ability to solve the types of problems that developers wanted us to solve.
hmm
In the cloud, at the same time, right? AI was maturing, and developers were seeing what's possible with computer vision. On the edge, we had nothing. A little bit of encoded, a little bit of OpenCV on Linux-based devices, but we really didn't have much in terms of AI. So we started working on some of the first open source projects for running machine learning models on microcontrollers.
hmm
And that was cool, right? We had a cool open source project. We helped start the TinyML Foundation, now called the Edge
hmm
AI Foundation.
hmm
And all's great, right? We have a demo running of MNIST on an STM32 microcontroller.
hmm
Problem with that is that there was only one engineer at Google
hmm
that could train a model from scratch. One. Everybody else ran the MNIST demo.
hmm
And MNIST on a microcontroller is kind of stupid, right? Without a camera, it didn't do anything. It fed in a dumb image example, and it classified it, and then did the next out of the
Yeah.
There was no camera, right? It was really a dumb demo. But it showed us that there's something here, right? We can really start to run machine learning models on microcontrollers, but the developer experience was horrible. It was really completely unusable for anybody but a deep ML researcher, a deep ML embedded researcher, right?
hmm
So Jan and I, my co-founder and I, working and Jan led that team, we're like, this is amazing, and it's never going to work like this, right? Developers are never going to go in industrial companies and be able to use this to do something real. It's just way too. So the gap between the difficulty of the tool stack and the developers that needed to actually build something with it, miles apart, right? Grand Canyon, other side. So that was really our pain point. We got super frustrated. We almost quit. So actually, that's an interesting story. We almost walked away. We're like, you know what? Let's go work on a different project. Because this is just like, didn't feel like anybody that was working in that space cared. They're just like, we wrote our research paper. Let's throw away the Python code and write the next research paper. We could care less whether the code works. Literally, that was the kind of the culture, because that's what people were motivated by. So we nearly walked away, but luckily at some point we just started brainstorming on like, you know what? Maybe there's like a persona mismatch. Maybe people are making these tools for the wrong people for the wrong reasons. And it turned out that was the case, right? People were making the tools for deep ML research scientists to write more papers. They weren't making tools for real engineers that work in companies, right? And so we set out with Edge Impulse. We left ARM. We set out with Edge Impulse to solve that problem, right? If we can bring the tools to millions of developers that work in all of the IoT industries, right? They have other jobs to do, right? They're solving problems in sensing for agriculture, or audio solutions for headsets, or biomedical wearable devices, or computer vision in industrial manufacturing, right? They have a job to do. They're trying to use machine learning to solve a problem, not try to build up the tool stack. So we set out to enable millions of those developers to use tools to go solve problems with their own custom data, use machine learning to go solve those problems, and deploy them to the edge. And that's always been our vision, right? Go democratize this technology for a lot of developers.
And so for you, you guys started off originally doing time series ML, which was like accelerometers, gyroscopes, and then microphones. And now you're looking at computer vision more seriously. Where do you think the growth area is on which of those verticals? Is it all of them, or is it one more important than the other?
I weight them pretty equally. I'd say that the reason we started working in microcontrollers, really think of it as like, what can we do with a microcontroller, which is sensor fusion on time series and some audio, was that we could win the market fast. We were the only people that could do that, and we could do it better than anybody else. So that's more of a like startup strategy thing than a technology choice. It's like, all right, there's a little gap in the market. It's not too big of a target to win that, so we can just go after it and do it. And once we win that, we go on to work on the rest of the problem space, which is MPUs and computer vision. So that's always been our vision, right? It's like we work all through all of edge compute. We're not that picky whether it's microcontrollers or MPUs or even like edge CPUs. They're all things that people use in industry to solve problems, right? It's just a tool. After about the first year and a half, we'd already solved a lot of the problems in time series and audio. So we did move on to work on computer vision. And that's been a few years now. Now I'd say that we've reached a state where time series has hit a kind of steady state where we have the tools we need. We know how to solve the problems. It's just deployment, right? Let's help people go get their data in, figure out how to deploy what kind of problems. So it's gotten into more of like a solution state, not we have to figure out the fundamentals, right, of the models.
Yeah.
Computer vision, on the other hand, there's a lot of new innovation happening because of transformers, a lot of new innovation happening with VLMs. We're doing a lot of new things with advanced computer vision models as we get more compute. We're pushing more, computer vision architectures on the high-end microcontrollers, what you work on a lot. So there's a lot of really interesting things happening in computer vision right now. Just maybe the state of where we are at AI algorithms, the state of the compute. It's gotten really interesting, and it's kind of a time of innovation. So we're investing heavily in that. But from a business perspective, I think there's pretty equal problems to be solved. And we do them in a multimodal way. And I think that's really the future, is that it's not just about computer vision or just about time series or just about microcontrollers or MPUs. We're going to mix and match this stuff. So many of the best edge AI solutions will be, sensor fusion plus computer vision to get the accuracy you're looking for on a manufacturing line, right? Don't depend just on the vision. look at a signal at the same time to make sure it's 99% certain.
Mm-hmm.
Same with audio, right? Can we use audio with computer vision to detect things that couldn't otherwise, or audio plus sensors? Multimodal is really the future of this, and so we're looking at a lot more multimodal workflows, and solutions, and model architectures in the future to solve problems that people are really coming up against, and sometimes needs a lot more different types of data to solve. So that's where I see the future.
Gotcha. Well, at that segue, I'd like to introduce two new tools that we're about to launch, or that we've launched to make this possible. So I'd like to first introduce the OpenMV Cam AE3. This is our smallest OpenMV Cam ever. It's 1 inch by 1 inch, and it features the Aleph Ensemble E3 processor and the OpenMV Cam N6. This is based on ST's new STM32 N6. And we have a more traditional OpenMV Cam-like feel with our removable camera modules and stackable shields and etc. What's amazing about these two new systems is, for example, with OpenMV Cam AE3, we're putting on it it's got the 200 gigaops, neural network processor on board. So just right off the bat, what is that? Literally 200 to 300 times more performance per ML. Just, again, 2 orders of magnitude, not one. Not 0, not 1, 2. So huge difference in performance. We were looking at different processors, and we noticed that there were a few CPUs that had linear speedups from our RT1060, which we launched last. But a linear speedup isn't going to cut it when you need to move to ML. You really need those, not even 1 order of magnitude, but 2 orders of magnitude performance increase. This new thing has 5 sensors on board. So when you mentioned multimodal, we've got a global shutter, 1 megapixel camera that can run at up to 240 FPS at VGA and about 30 FPS or so at full res. And so that's on board this little 1 inch by 1 inch module. Color global shutter, the ability to trigger, perfect for factories, automation, sensing motion. We've paired that with an accelerometer and gyroscope centered right behind the camera so that this thing can actually feel and sense vibration. It's also got a microphone on board and an 8x8 time of flight sensor. So 5 sensors in one package. All of those can feed into the neural network processing unit on board. And thanks to Aleph's novel chip design architecture, they put 13 megabytes of RAM on chip that is clocked at about 3 gigabytes a second. And so this means this thing doesn't need SD-RAM. It's basically like DDR4 memory as long as you keep your model sizes small. And then to execute the model, we actually have a new chip that is starting to appear. These are called OctoSPI flashes. And so the processor is actually you're able to store your entire model on a flash drive, and then the processor executes that in place. But previously, before, the fastest buses you would see would be QuadSPI, and that might be clocked at 133 megahertz or 166 megahertz for about 66 megabytes a second. Now we have OctoSPI, which is actually 8-bit DDR at 200 megahertz. On the Aleph Ensemble, it's only going to run at 100 megahertz max, but still that's 200 megabytes a second. And so, we're getting to, desktop PC hard drive speeds, basically, if you think about it. Nothing to play around with in terms of the bandwidth there. And so the MPU actually is able to receive the address of just where that model is sitting in flash, and then it executes it in place with 0 interrupts from the processor, more or less. This gives you incredible performance. In particular, we can run YOLO V5 on this little camera at a 60 milliamp current draw at 30 frames a second almost. So kind of unheard of performance. If you look at our OpenMV Cam H7, which was, I think our last, H7 Plus, which is our current model, that achieves about 0.3 frames a second on the same model, but draws 3 times the current. So we're looking at a 200 plus, what is it? Yeah, like a 100x speed up on the ability to actually run the model, and then 2 to 3x less power consumption.
Yeah, and this really opens up kind of the holy grail for many specialized computer vision applications, which is computer vision on battery.
Mm-hmm.
Running an AI model continuously, which is something we really were constrained before by Linux.
Mhm.
keeping all that memory alive, it's expensive, right? So a Linux-based design is always going to be very power hungry, very difficult to go to sleep, and duty cycle for battery. And
Yeah.
at the same time, our old microcontrollers, yeah, we had to run very small computer vision models. So now we can run larger computer vision models. I'd say we start to be memory bound now, right? Where we could go bigger, right? But we're probably going to run out of memory first before we run out of performance. If you're not
Yeah.
having to be at 30 frames per second, if we can run at 10, we probably can do a much larger model. But that's
Yeah.
an exciting boundary to work on, right? We can optimize these things more to be able to put larger and larger models, or just get more accuracy out of a model by making it more specialized. So maybe we look at less classes.
Yeah,
You know,
I can talk about that a little bit. It's like, so what we found is a model of about, so when I mentioned YOLO V5, that was the YOLO V5 Nano model that'll achieve 30 frames a second almost, about 28 actually currently, but there's still some optimization work that we can do. So we can probably get that above 30 once we fully optimize all the paths. But it's that's YOLO V5 Nano, so that's about 2 to 3 megabytes in size. So you can switch to a YOLO V8 small, YOLO V5 small model, and then that's about 8 to 10 megabytes, and that still fits on board the system. But then yes, you do see the frame rate fall by 3. So as you go with a larger and larger model, you basically just tank your frame rate. And so it really is a trade-off on what's the quality of the performance versus how good do you want the model, more or less.
that's okay, because I actually think in a lot of these battery powered systems, we're not in a hurry necessarily to get the experience result out, right? We're probably triggering,
Mhm.
wake up, right? Something happened, motion,
Mhm.
vibrate. We wake up, we take a few frames, we store, and then we can process those. And we're not in a big hurry, right, to try, because we're not necessarily on all the time in a battery powered application.
Yeah.
So I don't see that as an issue. What I do
Mhm.
see from customers is that they really want accuracy. They want the best possible model with the best accuracy for the memory that there is available.
Mhm.
Probably the trade-off we'll be looking at for a lot of these battery powered computer vision systems like this is, how can we build the biggest possible model that gets us the best accuracy? And then we're kind of tweaking on frame rate and other parameters to get the performance that we need. And then you start to make some trade-offs.
Yeah.
And so that'll be interesting as we see people build solutions with this. Like, what kind of models do they end up running?
Yeah, no, it will be. And we designed the AE3, for example, to have a few different features to make battery power really nice for folks. So one of the things we did first is, we tried to design every single component to have a low IQ, what is it? Low current draw, that's the word they use, IQ. Anyway, so pretty much this thing, when it's sleeping, every component was chosen to be as low as possible. We designed it by default with low power in mind. Right now, we're at about 500 microamps of current draw when it's in deep sleep mode. We hope to get that down to below 50, though. There's a lot of different settings that we have to play with on the AE3 chip, for example, to kind of bring that current draw down. But we're working on it and getting down there. And then for the N6, we also designed this with every of low power components available. And it has a more simple power switch architecture where when it goes to sleep, it just turns off the power rails for everything. This does mean it has less wake up abilities. So the AE3, for example, could wake up on microphone. It has a dual core processor system. And so when it's in sleep mode, you can actually have a second processor that has an NPU still running, and it could be running inference on the microphone or on the accelerometer or slash gyroscope. But thanks to that more complex architecture, a lot of different software features and switches that we've got to work through to really minimize the power consumption. With the N6, it just goes to standby mode. And in that mode, then all the power rails are off, and you just have a wake up then by basically your real-time clock or interrupt line pulling low. And what's nice about that then is you compare that with like a PIR sensor or the new TMOS sensor from ST that's like a smaller PIR sensor to wake up the system when motion is detected or etc.
It's exciting that we can already do this on the OpenMV boards as they are, right? Start to show how these battery powered applications work. I'm also excited about the new model architectures that are coming. I mean, YOLO V5 starts to be a little bit older.
Yeah.
New YOLO models have a bunch of licensing problems that aren't great.
Mhm.
So we've, as you know, been in development for our YOLO Pro architecture.
Mm-hmm.
It's interesting because we're specializing it specifically for industrial commercial applications. So not just for Cocoa,
Mm-hmm.
but instead for real data sets that we see out working with partners and customers all the time, so that we can get real performance, right? Performance on custom trained data. So you can kind of think of this a YOLO model for professional applications that you can really train with the data that's specific to your thing, rather than just having a pre-trained model that, you know, detects generic objects. That's not always so useful in real life, right? We have to get very specific, usually when we get into real customer cases. And so that's what YOLO Pro is designed for. And that will have models of the size of nano and small and very, very large
Mm-hmm.
to hit both the OpenMV, Aleph and N6 class devices, as well as the MPU side. When you have a lot of compute.
Yeah, what we did for the N6, by the way, to enable larger models is, so with the Aleph, we're only giving you 16 megabytes of flash drive space for models. You know, we have a 32 megabyte flash on board, and we're splitting it 16 megabytes for something called ROM-FS, which will allow you to have linear mapped file systems so you can execute things in place. And then 16 megabytes for a fat file system that allows you to have regular random files and image assets and whatever you want. That could be adjusted for specialized customers, and the flash chip size could also change. So like there are larger flashes you can use. We can't, though, of course, sell the default generic model that works for everybody's use case. So we tried to pick a sweet spot on what seemed good on performance, price, and reasonability. And then, you know, for custom folks who want to do high volume integration, we could obviously change these things for those customers. For the N6, what we tried to do to make it more flexible is it actually has an SD card attached to it. And this will allow you to load models off the SD card, just like our OpenMV Cam H7 Plus. And then we have 64 megabytes of something called HexaSpy RAM, which is a new IoT memory that gives you about 800 megabytes a second to store a model in. And so this means you could potentially go up to a standard YOLO-sized model in the 20 megabyte territory or so, and run that on board the system.
Interesting. I'm thinking about the largest model that we could potentially run on this device.
We tried to make it more flexible. Like,
Can we go to like a YOLO V5 medium?
as long as it fits in 64 megabytes, but you got to fit the model then and its activation buffers in that 64 megabytes. So that might be challenging, but it could be possible though. And then that unlocks like your ability to do really, really exact high performance inference on a microcontroller, and then the ability to go back to sleep. I would say you will likely have a frame rate that is not impressive though, so maybe 1 or 2 FPS or something. But if that's usable for the customer standpoint, that then, I mean, I think that scratches the itch then, because again, you can shut the system off. So it wakes up, takes a picture, computes what it needs to, and then goes back to sleep. And this allows you to get years of battery life.
Yeah, and for something like this where it's a very kind of singular event, and we have time to process what happened, that could be interesting to go with a much larger model that could be able to get the context as necessary.
Yeah.
So having that flexibility to run larger models, I think that is really important.
I mean, I think the whole battery life conversation actually is something that I want to just point out. You know, we've been talking to customers too, and a few things we're trying to integrate to support, by the way, is so both the OpenMV Cam N6 and the OpenMV Cam AE3, both of them have Wi-Fi and Bluetooth on board by default, so you have connectivity options. The N6 also supports a gigabit Ethernet PHY on chip on board the thing. And so the benefit of this is you can slap we sell a PoE shield, and so you can actually just attach a gigabit PoE shield to the back of the OpenMV Cam N6, and all of a sudden then you can go online, have it become a PoE camera. And again, gigabit, so it is at the same performance level for streaming data as a Linux-based system. It's also got an ISP and H.264 in hardware, so straight up, you can make it into an IP camera that is able to run ML and stream those results. It's incredible what the lengths ST went to. because they really have blurred the line between a microprocessor and a microcontroller, where pretty much everything you need to build a IP webcam, you can do it with an embedded system that has instant on boot time, the ability to go to sleep, and there's no need to have a huge software stacks and gigabytes of memory and gigabytes of storage anymore to handle the operating system. But what I wanted to say though is that we're also going to be offering LTE shields for both of these modules. So one thing for us is it's important to get these guys connected. So not just Bluetooth and Wi-Fi on board, but we'll be able to pair that with an LTE shield that gives you LTE and GPS at the same time. This will then allow you to connect these devices online, update data, and deploy them.
Very cool.
Now, the reason for why battery power is so important is that when I talk to folks who are wanting to deploy OpenMV cams into the wild, one of the, or at least computer vision in general, one of the biggest problems is wiring these devices up. I think you've seen that a lot, Zach, where the cost of the hardware, the cost of your software, the cost of everything that's necessary to make the application is dwarfed by having someone actually do a professional install job. And that can add so much friction.
Yeah, I agree. Like the ability to go and manage these devices is going to be one of your biggest problems getting into production volumes for many customers. If they can't manage them, they can't connect with them easily. Provision, update, all that's going to come into play as people start to deploy these in the field.
Yeah, but just like the fact of deploying them, I think, is something people don't quite understand, which is like, imagine if you had to go put a camera every 10 feet in Macy's or any big box retail store that wanted to track foot traffic or et cetera. If you had to run a PoE, power for those cameras or such, or run power, or just run in general any type of power wire, that, think about how many wires you're putting in the ceiling. Then those all have to go back to a single access point because you're not necessarily daisy chaining them. Maybe you can daisy chain them if they had a power wire, but then, if they have Wi-Fi and Bluetooth, for example, by default, it's a whole bunch of different devices to add to network switches and access points then. And so, when you think about just the complexity of putting hundreds of devices in one location, things start to get out of hand. Like, let's say you wanted to put these in parking decks to monitor people coming and going, or et cetera. All of that starts to become a problem, especially when you think about the conduit that's needed. If you needed to run power wires, conduit for PoE cable, that starts to add a lot of money to the deployment of the system. And so being able to run on batteries presents you a new option, which is you can actually say, let me just take some D batteries. Not even like LiPos, because LiPo batteries kind of explode, catch fire. People are a little bit hesitant to put those all in industrial facilities. But now we're looking at, can we run these devices off of 3 alkaline D batteries? We will have support for something called a buck boost regulator on board our LTE shields for our systems, which allow you to run off of alkaline batteries from about 4.5 volts down to 1.8. And this gives you the ability to kind of last the whole range of literally cheap alkaline batteries, $1 each. And thanks to that, now you can make a device that can be deployed, connect to cellular to get online, and doesn't need any physical wiring, and then can connect to Edge Impulse for updates, provisioning, and so on and so forth.
Where do you see the future of these devices going now that we have more compute? Do you see it in more innovation from the developer community on the applications that they're running? Or is it somewhere else that we need to work on improving this? So how do you see your roadmap going forward around this?
Yeah, I mean, there's going to be, I think the biggest thing we want to see is just deployment, people getting these devices out into the real world. Right now, a lot of the models that are currently available will allow people to start to scratch the itch of having large, scale deployment of these things everywhere. I think, though, we really need to come into, to work with Edge Impulse to build out more useful models like anomaly detection, for example, where a lot of customers, it's not really about, hey, can I detect an object and do some business language about that? It's really more, I have a static scene. Can you tell me when something important has changed in there? I think what people really want to see is a build out of more of the vision transformer kind of models, where we move from detection of random classes, objects, and such, and more to just, here's a picture, figure out what's important inside of it, and produce the result we need.
Well, I think we're going to see both. It'll take some time before we get that to a microcontroller. On the anomaly detection side, we of course have had FOMO anomaly detection as an architecture out for some time. We're just getting ready to launch our new high definition version of that for all the developers. So I think that'll pair really well with these higher end OpenMV boards. So we can scale out resolution in a big way, and that will get like much more precise about little small problems, small anomalies like cracks, right? It's not many pixels that makes up a crack. Or we've looked at like anomalies on pins for electrical components. Well, pins aren't very wide. So if you don't have resolution, you're not going to see the pin. So that's something that's coming that will drive more compute consumption on devices. I think super useful for everybody. You only need good data, right? You don't need any anomaly or any other classes. You can run it as a single anomaly detector just on good vision data, good examples, huge numbers of applications. So that's exciting. When you talk about one-shot models, so things that we can do with transformers, which really means getting into vision language models, so very large models that have a vision front end. So we can feed in an image in practice to an LLM, analyze what's going on without having trained it on anything. In theory, yes, works in the cloud pretty well. We're only starting to see the first deployments of this on edge, on big edge compute. So you're talking about 50 to 100 tops, very large amount of memory. And the performance is still poor, right? We're not going to keep up with real-time frame rates. So then we have some interesting problems, right? Like, how do we decide what images to feed into a VLM? We can't feed it everything all the time, right? We're just going to drown this model, and the things we get out of it might be very confusing, right? Like random stuff that the camera starts to see and describe, and it might get it wrong, right? You hallucinate about something, it's going to confuse everybody. So my vision is that you really need to start to create hybrid architectures, like small, large agent models, where it's like, all right, we're going to cascade from small model, and that could be FOMO visual anomaly detection, right? So you put a FOMO AD model in front. We could run that in an OpenMV Cam. So run that in an OpenMV Cam. You kind of choose what you're looking for, right? Like now something interesting has happened, right? There's a vehicle here, right, in front of me. Now I want to take an image of that. That's very selective, right? High quality. Maybe we take a few, we choose the one that's the highest quality. Then we wake up the large, 100 top processing unit and feed that image over, right? Now it might take seconds or even longer for that to process, but fine, because I've chosen the one image that I'm interested in. I can take that process and get a description of that vehicle, right? That very specific, like, what is this vehicle? Is there something missing, right? What's the year, the model? There's a lot you could get out of an image of a vehicle, but you have to do it extremely selectively, right? When you're in an embedded system. So this is something we're going to have to get good at. I think it's new for us in edge compute systems. Like, how do we deal with these very large Gen AI models when we can't run them at real time? So these kind of cascading architectures are going to be interesting.
Yeah. But I also think, now that we've seen stuff like DeepSeek happen, there's probably, the second we release this new hardware, that people start getting these OpenMV cams into their hands, I think there's going to be some pressure on researchers to start thinking about how they can shrink these models down, because you're definitely not fitting the large vision transformer models on small battery powered systems. And I think there's going to be a huge demand for that. And so we expect to see that new silicon will come into play and new techniques and such to make this possible. So
For
before
sure.
we go,
The
I wanted
research,
to do it.
the final frontier there. I think there is going to be new research on what can you
Mhm.
do with this compute and what can you do with transformers and memory and a lot else. But it's not going to be what people see from Gen AI today in the cloud. So I think it's going to be important to set expectations of what is it we want to achieve, right? What's the problem you want to solve? You're not going to get a generic one shot. It understands the entire world, right? On an N6. So what is that one problem we really want to solve very well and we can't solve today with today's architectures? Let's invest the research in that. So I do think that'll be interesting.
Yeah, no, absolutely. So before we go, as I was mentioning, I just wanted to share a little demo of the OpenMV Cam AE3 running. And let me just find my, for some reason, the share button is not finding my, okay, there we go. Cool. So this is OpenMV IDE. It's how you program the OpenMV Cam. And so what we've got running here is YOLO V5. This is trained by Edge Impulse. And so we've got this running on the OpenMV Cam AE3. So we've still got a lot of work to do on the image quality. This is really just raw Bayer coming off the camera. We'll be improving that as time goes on. But just out of the box demo, as you can see, we've got a decent frame rate streaming to the computer, and it is finding me in the picture at about 16 frames a second or so. No, 18 actually, when streaming data. And then if we were to reduce the system load by taking off the computer, it actually hits about 20 frames a second when it's operating without having to, have the PC being touched by it.
Nice.
So it is really a new frontier on what we can do with these models because, again, this is 60 milliamps of current draw, and it is running YOLO on board. This was previously completely not possible at all at any real-time frame rate. And so we're just super excited about what this means for, everybody, like what people can do. This particular YOLO model was trained on the FLIR pedestrian data set using thermal cameras, but also vision. So it's not the same as the regular YOLO V5, which has a more, a better COCO data set with people closer up. So that's why it struggles when I get too close to it. But still, we trained a custom YOLO model thanks to Edge Impulse and their support for doing that, and have it running on board a system again at a real-time frame rate.
And I think that specialization is important too, that ability to go train a model on specific data, because again, in a real application, you're going to have something very specific you're looking for. And so that's important to be able to go do that and train it. So glad to hear that that's working for you when you're wanting to create a model and deploy it.
Yeah, and then one other thing I wanted to show is we also have the FLIR boson. This is the high-end thermal camera for the N6. And so this is why we have these, this specialized YOLO model was actually to produce a YOLO model that can run on thermal data, since it's slightly different from, let me just, here we go. So similar script that we have running on board, and let me just see if it works. Oh, nope, okay, wrong. I got a few different N6 cameras lying around, so I just got to grab the right one on my desktop. Give me 1 second. Alrighty. I inserted this board into here. Okay, I think I got it out. All right, good to go. You got to prepare for these interviews. Yeah, so we showed this demo off at CES actually, and it was a hit. People really like to see that this was possible on an MCU. Okay. All right, I think it's working. Okay. So the ultimate thermal vision, detection. And so this is where things really get cool. Is we are running a FLIR boson. This is a 640 by 512 thermal imaging sensor, and so we're able to run this model onboard this using the N6 and have thermal tracking. And this is, this is where you can really deploy an N6, for example, in a, in an outdoor environment, in a real use case, in an industrial use case, and have it provide useful feedback. And so this can be running YOLO Pro, this can be running FOMO AD, whatever models you need, we can have this and deploy to a customer site. And so FLIR bosons are expensive thermal sensors. They're not cheap, but this same technology works on the FLIR lepton too, which is a much more inexpensive sensor. For professional customers, though, typically we see that they'll pay a thing a little bit larger to actually get the results they want.
Yeah, the quality looks amazing. I mean, I can see how we can train models on this for accuracy as well.
Yeah, and so note that the performance you saw there of 15 FPS or so, that was literally just because we're following that 2 iron bow method. That was doing the color conversion, and we haven't yet optimized everything, so that was currently not Cortex M55 accelerated. That was just using standard C code. And so once we go through our code base and start doing Cortex M55 optimizations and using the GPU for everything, we'll be able to pretty much get the frame rates all over the place. So you see now in just pure grayscale mode without recovering the image, it's really 30 frames a second. And then if we disable the mode, straight into IDE, we're actually going to see this shoot up to about 43, 55 FPS or so for running this model. And so, yeah, it's, the N6 is quite a bit faster, the same model than the AE3. And there's still a lot of more optimization fruit to pick to get these things to go up and up on the speed and performance. So we hope to get this up to like 60 FPS or so, which is the actual frame rate from the FLIR boson.
And so we could run a small model at maybe 10 frames per second.
Yeah, 10 frames a second would be where I think you would be at. We have one customer that was going to be happy with just 5. And so they wanted to run a larger model to really detect things very accurately. And so we expect that this system will really deliver for a lot of customers. And what's crazy here is that if you think about this performance level and speed, this is actually outperforming a Raspberry Pi 5, just as a bare board, for example. This, this really puts a microcontroller, well, obviously, any workspace system has an NPU much faster. But for anything that doesn't have an NPU, this is more performant now, and we'll be able to do a better job for ML and AI.
Super exciting. I mean, the developer experience here is really easy, so that opens it up to a lot of new people to do embedded computer vision development.
Yeah. Anyway, that is what I wanted to show. Thank you for taking the time to talk to me, Zach. Is there anything else you wanted to talk about before we go?
A lot of new toys. That's super exciting. No, I just say stay tuned. We got a lot of stuff coming now in Embedded World. We're just a couple weeks away from Embedded World, so a lot of new cool stuff coming there. So that's it.
And
stay tuned. We'll be talking more about LLMs and what's going on at the very high end and how that works. So that'll be something to show off. And then, of course, we'll talk more about our new YOLO architecture. Yeah, and just to let everybody know, the OpenMV Cam N6 AE3 Kickstarter is currently running. We're launching it during the Embedded World, and we'd love if you can come on and back us on Kickstarter and help support the OpenMV Cam AE3 and N6. Thank you for watching. Thanks for having me.